Hello, and welcome to the CurioClips channel. For 1,600 million years ago, the Earth had not yet formed, but it was getting close. Gravity was pulling together the bits of dust and rock that would eventually form our home planet, and those bits were flying through space at up to 30 miles per second. As they smashed into one another, they released a burst of energy equivalent to 300 million atomic bombs going off, giving us a brief glimpse of the unbelievable power of our humble planetary beginnings. That process of building up layers upon layers of material around a core took about 10 million years. And as gravity pulled more and more stuff toward the still molten rock at the center of the growing sphere, heat built up. This heat, combined with radioactive elements deep inside the Earth, heated the planet to 9,000 degrees Fahrenheit, almost as hot as the surface of the sun. It was so hot that the heavier elements like iron sank to the core, while the lightest elements like hydrogen and helium floated away into space. In fact, scientists think that the Earth lost half of its mass during this stage of its life cycle. So what we have now is mostly what was left over after all that gas escaped: a hot, gooey, swollen mess of silicate minerals and a bunch of leftover iron. But under that gooey exterior, something cool was happening. The heavy elements at the core were undergoing a process called fusion. They were combining to form larger, heavier elements and releasing energy as they did. That energy created a magnetic field that extended hundreds of miles out from the planet's surface and protected the rest of the Earth from being blown away by the solar wind. Magnetic fields still do this for us today, which is why the time period from 4,530 to 4,000 million years ago, when Earth's magnetic field first turned on, is called the Great Oxidation Event. Meanwhile, the rest of the Earth was busy creating an atmosphere, oceans, and maybe even life itself. For 1,400 million years ago, the Earth had cooled enough for solid rock to start raining down onto the surface. These rocks contained gases that had been trapped inside the planet since its formation. As the pressure from the atmosphere forced these gases out, they formed a thick, cloudy blanket around the Earth. Water vapor, carbon dioxide, nitrogen, and some oxygen were among the gases released, along with others that are poisonous to us today, such as hydrogen sulfide and sulfur dioxide. Even though conditions on Earth were still pretty rough, life of some kind had emerged. Billions of years later, we still don't know exactly how life began or what the very first living things were like. But we do know that the oldest fossils we've found so far date back to the Pacifist Eon, specifically to a place called Isua in Greenland. These ancient fossils are evidence that life was already on the way to becoming complex. After all, there wouldn't be any fossils if it wasn't for the development of hard body parts like shells and skeletons. So before this, life might have looked more like single-cell blobs. And it's possible that the first steps of the evolutionary ladder took place during the Pacifist Eon. Oceans also played a huge role in setting the stage for life as we know it. You see, water vapor from Earth's early atmosphere condensed into clouds and fell to the ground as rain. Over time, this rain filled in the low spots on the surface, forming vast, deep pools. But where did all that water come from? Well, it turns out the stuff that makes up our solar system once existed in a giant cloud of gas and dust. And that cloud didn't just include materials that would eventually become Earth. There was plenty of hydrogen floating around. And when that hydrogen formed water with oxygen, it left behind a whole lot of extra oxygen that could have contributed to the Earth's early atmosphere. In other words, our oceans may have helped create the oxygen-rich environment that allowed complex life to thrive. By the end of the Pacifist Eon, Earth looked pretty similar to how we know it today, except without any continents. The surface of the planet was basically one giant ocean. And it wasn't until 4 billion years ago that granite, the world's first continental crust, started to appear. How did this happen? Well, you know all that hydrogen and helium that escaped from the Earth's atmosphere in the first few million years of its existence? It turned out that stuff didn't stay in space for long. It rained back down to Earth in a deluge of supernovas. When our sun and the rest of the stars in the Milky Way exploded, they threw huge amounts of material into the vast emptiness of space. Much of this material was hydrogen and helium, which eventually formed new stars and planets. But some of it landed right here on Earth. All told, scientists estimate that at least 2 giant supernovae hit our planet during the Hadean Eon, bringing with them all sorts of interesting elements. One such element was aluminum, which can combine with silicon to make quartz, a major component of granite. Other elements included calcium, titanium, and phosphorus. These elements formed minerals that created pockets of solid rock beneath the surface. And once those pockets got big enough, gravity ripped them apart and sent huge chunks crashing down to the surface. While some of these chunks probably just bounced off the liquid outer layer and fell back down into the ocean, others may have landed in just the right spot to stick. These lucky pieces of continental crust became part of the foundation of the land masses we live on today. As the Eon wore on, more and more of these massive meteor impacts lit up the sky. Some were big, like the one that killed off most of the life on Earth 2.5 billion years ago. Others were smaller, but no less significant. For example, the Vredefort impact in South Africa was only about 5 miles wide, but its effects were felt across the entire planet. Debris shot up into the atmosphere, and within weeks had circled the globe. So widespread was the devastation that scientists think the Vredefort impact may have triggered an ice age. But even that couldn't stop the progress of life. The first photosynthesizers appeared during the Paleoproterozoic era, changing the course of history forever. Here's how. You see, up until this point, life in the oceans was anaerobic, meaning it didn't need oxygen to survive. But as photosynthesis took hold, more and more oxygen started floating around in the atmosphere. At first, this oxygen reacted with other elements in the atmosphere and formed ozone, which created a protective layer that shielded Earth from the sun's harmful ultraviolet rays. Meanwhile, the oxygen that stayed in the atmosphere slowly changed the planet's chemistry. In fact, the increase in oxygen levels caused so much chaos that it's known as the Great Oxidation Event. Most of the anaerobic organisms died off, but a few stuck around and adapted to the changing times. Those survivors thrived thanks to the oxygen produced by photosynthetic bacteria, fungi, and other organisms like them. And because of their success, aerobic organisms, animals that use oxygen to survive, were able to evolve and take over the oceans. So in a roundabout way, the arrival of photosynthesis set the stage for our emergence millions of years later. Over the next few billion years, the pace of evolution accelerated dramatically. Multicellular organisms appeared and went extinct. New species evolved and radiated. Fish developed hard parts like bones and shells, allowing them to flourish in the oceans. Then came the first terrestrial plants and animals, followed by the first forests and the first large animals. Throughout all this, Earth was changing too. Continents drifted, mountains rose and fell, volcanoes erupted, and more oxygen entered the atmosphere. By the end of the Proterozoic Eon, the planet looked a lot like it does today, except for one key difference: the lack of any life on land. But that wouldn't last for long. Just over 500 million years ago, animals made the transition from water to land, and life on Earth would never be the same. If you'd like to learn more about the Paleozoic era, you can check out my video about it here. Thanks for watching. See you next time.